Nuclear and particle physics have been a very important part of the entire subject of physics, and its practitioners have won an impressive number of Nobel Prizes, maybe the largest number compared to any other topic in physics. The study of subatomic particles and their properties has given scientists a better understanding of the nature of matter and energy, and of course the origin of universe. Despite more than a century of research, the subject nuclear and particle physics remaining exciting and vibrant, with many interesting phenomena still being discovered and problems awaiting solutions. It was a common practice to teach the two subjects together, and the scheme was followed by many Indian universities till recently, when the topic becomes so vast that no single course can do justice to both. Thus, teaching them separately become inevitable, and it is advisable to include the two topics as separate courses in subsequent semesters. To understand the basic concepts of particle physics, fairly good knowledge of quantum mechanics and nuclear physics is required. However, in this lecture series, the required knowledge of quantum mechanics and nuclear physics is kept at a very basic level that the students in graduate class can follow them easily. Students are advised to read textbooks for more information and clarity, because no lecture class can be the replacement of a standard textbook, and the lecture notes are not going to fill up the gap of understanding any subject from its basics to advanced level. In the first lecture, we study the classification and properties of elementary particles, which are the building blocks of universe. There are many good textbooks available for various levels, and the students can select according to their requirement. A few graduate level textbooks is listed below. The first one, by Griffiths, is extremely nice, and the author, through his lucid way of presentation, make the subject very interesting. The concept that the world is made up of fundamental particles has a long history. The idea put forward by Dalton that atoms are the indivisible building blocks of matter can be considered as the first convincing suggestion in the history of particle physics. However, the observation of characteristic spectra of elements suggested that atoms have their own internal structure. The discovery of electrons by J.J. Thomson, followed by Rutherford scattering experiment using alpha particles, proved that atoms consist of negatively and positively charged particles. Then the scientists came to a comfortable situation with the assumption that the complete universe is made up of some 90 plus elements, with the support of chemistry that was developed to a remarkable level by that time. It was logical to believe that the atoms of different elements consist of different number of electrons revolving around the nucleus, which has a heavier mass and comprising an equal number of positive charges. Later, it was discovered that nuclei consist of neutrons and protons. At this stage again, a satisfactory situation was evolved. All matter appeared to be composed of various combinations of three elementary particles, the neutron and proton held together by strong force, and electrons revolving around it, satisfying Coulomb's law of forces and quantum conditions. However, the confidence was short-lived with the discovery of more number of elementary particles, neutrinos, mesons, and quarks. The probing continued, leading to the discovery of muons and pi mesons, followed by many other related mesons and even larger number of particles associated with the neutrons and protons. At present, the number of particles is too large and difficult to classify in a unique way, but is still possible to assume that the universe may be possibly composed of various combinations of some set of elementary particles known and unknown till today. More than 200 subatomic particles have been detected so far, most of them highly unstable, existing for 1 millionth of a second or less, and are produced as a result of collisions in cosmic ray reactions or particle accelerator experiments. Electrons and quarks containing no discernible structure, they cannot be reduced or separated into smaller components. So, it is reasonable to call them as elementary particles, though the name in the past was mistakenly given to the particles such as proton and neutron, which we now know that has a complex structure containing quarks. The term subatomic particle refers to both true elementary particles such as quarks and electrons, and also to the larger particles that are formed by quarks. There exist matter particles and force or field particles. Quarks and leptons are matter particles, whereas photons and gluons are force particles. In the standard model, all of the matter particles are fermions, whereas force particles are bosons. These two classes of particles have different symmetry properties that affect their behavior, and the details will be discussed in the subsequent lectures. It is important to mention four kinds of natural forces here. Gravity and electromagnetism are well known at the macroscopic level. The other two forces act only on subatomic scales, indeed on subnuclear scales. The strong force binds quarks together within protons, neutrons, and other subatomic particles. Rather, as the electromagnetic force is responsible for holding bulk matter together, the strong force keeps protons and neutrons together within the atomic nuclei. Unlike the strong force which acts only between quarks, the weak force acts on both quarks and leptons. This force is responsible for the beta decay of a neutron into a proton, and also for the nuclear reaction that fuel the sun and other stars. Every particle, massive or massless, is subject to gravitational interaction. Particles that are electrically charged experience electromagnetic interaction. There is no classical analog for the strong interaction responsible for binding nucleons inside a nucleus, and also weak interaction which figures itself in decay process. These two are short range forces, unlike electromagnetic and gravitational forces which are long range. All the fundamental interactions are possible by exchange of some elementary particles, bosons. These particles are known by various names such as messenger particles, force carriers, intermediate bosons, and gauge bosons. Many a times, when these particles are involved in interactions, they cannot be observed because they act as virtual particles. There are various ways for the classification of elementary particles. We know that there are charged and neutral particles. Electron is the first particle discovered and is negatively charged, followed by protons, the positively charged particle, and a neutron with no charge. Based on spin, particles can be classified as fermions and bosons. Fermions with half integral spin and bosons with integral spin. Particles can also be classified based on the interactions like strong, weak, electromagnetic, and gravitational. These forces of interaction are mediated by intermediate particles or exchange particles. Photons are the exchange particles of electromagnetic radiation, gluons for strong, W and Z bosons for weak, and gravitons for gravitational interactions. Another fruitful method for the classification of elementary particles is perhaps based on their mass. Leptons for light particles and hadrons for heavy. Hadrons are further classified into mesons and baryons. Baryons are the heaviest particles known, followed by mesons. Pions and kaons are examples for mesons, whereas protons and neutrons are examples of baryons. Electrons and neutrinos are examples for leptons. One of the major limitations of the classification based on mass is that an important class of particles, photons, is not included in the above group. This is anyway expected because the above classification is based on mass and photons are energy particles with a restive mass equal to 0. At the same time, massless particles such as neutrinos crept into the group through leptons. This means that whatever be the method of classification, some particles are always left or some may find in different groups. For example, classification based on spin, some bosons and fermions share certain common properties. Classification shown in the next slide is more elaborate and give better insight into the field of elementary particles. Photon is the first particle identified with almost complete properties known first as electromagnetic waves from the study of spectral lines and then as particles. Actually, entire electromagnetic spectrum from gamma rays to radio waves was well known much before their identification as particles. Leptons are classified into electrons, muons, tauons, and neutrinos. Electrons are negatively charged particles with spin half and infinite lifetime. Muons are elementary particles similar to the electron with an electric charge -1 and a spin of half but a much greater mass, approximately 207 times that of the electron. Lifetime of muon is 2.2 microseconds, which is very high compared to other unstable particles. Tauons are negatively charged particles -1 with a spin half similar to that of electron, mean life about 2.9 multiplied by 10 to the power -13 seconds and 3477 times heavier. Tau is the only lepton massive enough to decay into hadrons, particularly into pions. And finally, neutrino is a lepton with a spin half but has no electrical charge and has very small mass, which might be even 0. Neutrinos are one of the most abundant particles in the universe, and because they have very little interaction with matter, it is incredibly difficult to detect them. Discovery of neutrino has far-reaching consequences in nuclear physics, including the theoretical explanation of beta emission, conservation of angular momentum, etc. There are 3 kinds of neutrino: electron neutrinos, muon neutrinos, and tauon neutrinos. Hadron is any member of a class of subatomic particles that are built from quarks and react through the agency of the strong force. All observed subatomic particles except the gauge bosons and the leptons are hadrons, except for protons and neutrons that are bound in the atomic nuclei. All hadrons have short lives and are produced in high energy collision of subatomic particles. The other 3 basic forces of nature also affect hadron behavior. That is, all hadrons are subjected to gravitation. Charged hadrons obey laws of electromagnetism, and some hadrons break up by the way of weak force, as in radioactive decay, while others decay through the strong and electromagnetic forces. The hadrons are classified into mesons and baryons. Mesons are further classified into pi meson, eta meson, and k meson. Baryons are classified into nucleons, hyperons, and resonances. Nucleons include protons and neutrons, whereas sigma, omega, cascade, and lambda are 4 types of hyperons. In particle physics, resonance an extremely short-lived phenomena associated with the hadron that decay via the strong nuclear force. This force is so powerful that it allows resonances to exist only for that amount of time
light to cross each
such object, say nucleon distance. A resonance occurs when the net energy of the colliding subatomic particles is just enough to produce its rest mass, and the strong force then causes to disintegrate within nearly 10 to the power minus 23 seconds. Properties of the subatomic particles and important interactions will be discussed in detail in the subsequent lectures. The entire list of elementary particles is grouped into 3 generations of matter and their force carriers. To explain 3 generations of matter, we need to understand the Standard Model in particle physics. Standard Model explains how the basic building blocks of matter interact and governed by 4 fundamental forces. Standard Model is the combination of 2 theories of particle physics into a single framework to describe all interactions of subatomic particles except those due to gravity. The 2 components of the Standard Model are electroweak theory, that is, the theory which describes the interactions via electromagnetic and weak force, and quantum chromodynamics, that is, the theory of the strong nuclear force. Both these theories are gauge field theories which describe the interaction between particles in terms of exchange of intermediate or messenger particles that have 1 unit of intrinsic angular momentum, or spin s is equal to 1. In addition to these force-carrying particles, the Standard Model encompasses 2 families of spin-half subatomic particles that build up matter. These particles are the quarks and the leptons, and there are 6 varieties or flavors of each related in pairs in 3 generations of increasing mass. The 6 quarks paired in 3 generations, the up quark and the down quark, forms the first generation, followed by the charm and the strange quark, then the top and bottom or beauty. Quarks also come in 3 different colors and only mix in such a way as to form colorless objects. The 6 leptons are similarly arranged in 3 generations: the electron and the electron neutrino, the muon and the muon neutrino, the tau and the tau neutrino. The electron, the muon and the tau all have an electric charge and a sizable mass, whereas the neutrinos are electrically neutral and have very little mass. Everyday matter is built from the members of the lightest generations, the up and down quarks that make up the protons and neutrons of atomic nuclei, the electrons that orbit within atoms and participates in binding atoms together to make molecules and more complex structures, the electron neutrino that plays a role in radioactivity and so influences the stability of matter. Heavier types of quarks and leptons have been discovered in studies of high energy particle interactions, both at scientific laboratories with particle accelerators and in the natural reactions of high energy cosmic ray particles in the atmosphere. Mass, charge and spin associated with each particle is shown in the corresponding cell. We can see that the first column shows the first generation of matter and has the lowest mass. The second column, the second generation with the intermediate mass, and the third column, the third generation with the highest mass. The corresponding antiparticles are shown in the next three columns. Field particles or force carriers, gluon, photon, and W and Z bosons are shown in the seventh column. In the last column, we have Higgs bosons. The pictorial representation of quarks, leptons, and gauge bosons are shown here. Proton is made up of 2 up quarks and 1 down quark, whereas neutron contains 2 down quarks and 1 up quark to make its charge equal to 0. Higgs bosons is a fundamental particle associated with the Higgs field, a field that gives masses to fundamental particles. Higgs field is different from other fields such as electromagnetic field. First, it has no spin, that is S is equal to 0. For other vector fields, S is equal to 1. Higgs field is a scalar field. Further, it has an unusual property, that is, its energy is higher when the field is 0 than when it is non-zero. The standard model has proved a highly successful framework for predicting the interactions of quarks and leptons with great accuracy. Yet, it has a number of weaknesses that lead physicists to search for a more complete theory of subatomic particles and their interactions. The present standard model, for example, cannot explain why there are 3 generations of quarks and leptons. It makes no predictions of the masses of the quarks and the leptons, nor of the strength of the various interactions. Physicists hope that by probing the standard model in detail and making highly accurate measurements, they will discover some way a more complete theory known as grand unified theory, which uses a single theoretical structure to describe the strong, weak, and electromagnetic force. However, grand unified theory will still not include gravity. The problem here is that theorists do not yet know how to formulate a workable quantum field theory of gravity based on the exchange of graviton, the field particle, still to be discovered. Thus, finally we have all ingredients of matter grouped into 6 leptons, 6 quarks, and a few field particles to create the entire universe. The matter energy content of the universe is shown in this picture. Matter is 30.6% of the universe matter energy composition, in which 30.1% in the form of dark matter. Only 0.5% is in the mass of stars, and 0.03% of that matter is in the form of elements heavier than hydrogen. The rest is dark matter, a component of the universe whose presence is discerned from its gravitational attraction rather than its luminosity. 2 varieties of dark matter have been found to exist. The first variety is about 4.5% of the universe and is made of the familiar baryons such as protons, neutrons, and atomic nuclei, which also make up the luminous stars and galaxies. Most of this baryonic dark matter is expected to exist in the form of gas in and between the galaxies. This baryonic or ordinary component of dark matter has been determined by measuring the abundance of the elements heavier than hydrogen that were created in the first few minutes after the Big Bang occurred 13.8 billion years ago. Dark matter makes up 30.1% of the matter energy composition of universe. It is indispensable to introduce Femen diagrams to proceed with the study of elementary particles. Femen diagram, a graphical method of representing the interactions of elementary particles invented by American physicist Richard Feynman and introduced during the development of the theory of quantum electrodynamics as an aid for visualizing and calculating the effects of electromagnetic interactions among electrons and photons. Femen diagrams are now used to depict all types of particle interactions. It is a two-dimensional representation in which one axis, usually the horizontal axis, is chosen to represent space, while the second vertical axis represents time. Straight lines are used to depict fermions such as electrons and wavy lines for bosons such as photons. On a conceptual level, fermions may be regarded as matter particles which experience the effect of a force arising from the exchange of boson, the so-called force carriers or field particles. At the quantum level, the interactions of fermions occur through the emission and absorption of the field particles associated with the fundamental interactions of matter, in particular the electromagnetic force, the strong force, and the weak force. The basic interaction, therefore, appears on a Femen diagram as a vertex, that is, a junction of three lines. In this way, the path of an electron appears as two straight lines connected to a third wavy line where the electron emits or absorbs a photon. Anyway, the selection of space-time axis is not unique. Certain authors use horizontal axis to represent time. Femen diagrams are used by physicists to make very precise calculations of the probability of any given process, such as electron-electron scattering. For example, in quantum electrodynamics, the calculations must include terms equivalent to all lines representing propagating particles and all the vertices representing interactions as shown in the diagram. In addition, since a given process can be represented by many possible Femen diagrams, the contribution of every possible diagram must be entered into the calculation of the total probability that a particular process will occur. Comparison of the results of these calculations with experimental measurements have revealed an extraordinary level of accuracy, sometimes with an agreement to 9 significant digits. The first figure shows the Femen diagram of the interaction of an electron with an electromagnetic field. The basic vertex V shows emission of a photon by an electron. The second figure shows one of the simplest interactions between two electrons. The two vertices V1 and V2 represent the emission and absorption respectively of a photon. Femen diagram of the annihilation of an electron-positron pair is shown in the third diagram. The annihilation of the particle-antiparticle pair leads to the formation of a muon mu minus and an anti-muon mu plus. Both antiparticles E plus and mu plus are represented as particles moving backward in time. That is, the arrowhead is reversed. Femen diagram of a complex interaction between two electrons involving four
vertices
V1, V2, V3, V4 and an electron-positron loop is shown in the fourth diagram. This is a typical Femen diagram for elastic and inelastic electron-proton scattering. The space coordinate is the ordinate and the time is the abscissa. The electron and the proton approach each other and exchange a virtual photon after which the electron goes off in one direction and either the proton or some group of particles of net mass W goes off in the other direction. In the inelastic case, the electron's energy changes in the interaction from E to E prime, with the virtual photon carrying off the energy difference E minus E prime. Large amount of materials are available in the internet, published by famous laboratories, university websites and reputed authors. For example, Physics for 21st Century, Building Blocks of Matter. Students are requested to utilize these materials for their studies and for a better understanding of the subject. Forthcoming lectures will explain properties of elementary particles and their interaction with the support of necessary theory and experimental data.